of arrays, single-dimensional arrays, and of search. That differs from the final exam, which will contain all the material in the course, including multi-dimensional arrays and sorting. So if you think about the topics covered in the class, we've got all the stuff for the first exam, all the stuff for the second exam, in the final exam, and in the third part of the course, we have before the third exam, we have single-dimensional arrays and search, and after that, we have multidimensional arrays and sorting. So we'll talk about multidimensional arrays and sorting at some point before we actually have the third exam, and we'll talk about it after the third exam, of course. But those topics will not be covered until the final exam. So you can think of the final exam as being essentially cumulative of the course, except for some additions with multidimensional arrays and sorting. So today we're going to talk about the second major topic relating to the third exam, and that is searching arrays. Now, there are many things that you can do when you want to search for something. And as I said in an earlier lecture, search is a fundamental principle of computer science. The reason why search is a fundamental principle of computer science is because search is something that we do in many, many different contexts. One context that you might find unusual is actually artificial intelligence. Artificial intelligence is actually the very clever application of search. What software is doing when it pilots an automated car, what it does when it recognizes images, or when it suggests friends to you on Facebook, it is using algorithms that have been refined through artificial intelligence, and that refinement is simply the tuning of parameters, lots and lots of independent parameters that govern how those algorithms work. If you think about what makes a good set of parameters different from a bad set of parameters, that is simply a search for the best set of parameters. And artificial intelligence is indeed simply a search through very large dimensional spaces in order to find ideal sets of parameters and ideal values for things. That all starts, that entire scope of research and technological development all starts with very basic searches, starting with the two most basic possible searches that you can learn, which we're going to see today. And that's linear search and binary search. The reason why we learn these two searches and not the many, many other kinds of searches there are is because the linear search and binary search illustrate two different possibilities that can be achieved with searching that are qualitatively different. So linear search is a search that you perform when you look through an array by evaluating every member of the array in order. You can generalize that to thinking about search in terms of considering every member of some set in some order to find a particular element or a superlative element. So finding the tallest person in a room involves searching through the set of people, evaluating their heights, and finding the person that is superlatively tall. Linear search differs from binary search. Binary search is predicated on the assumption that you have an array that is sorted, and in the case where it's an array of numbers, then what that means is that you have the numbers from smallest to largest, or largest to smallest in the array. Because binary search assumes that it has a sorted array, it differs from linear search in that it has underlying assumptions. And it exploits the fact that it has this sorted array by not considering every member. So what binary search does is it divides and conquers. It examines one half of the array, and if it doesn't find what it wants, it examines the other half. And then when it finds what it wants, or if it decides that what it's looking for is within one half of the array, it takes that half and repeats the binary split again and again until it finds the thing that it wants or decides that it's not there. The result is that you have a search that can run much faster than linear search because it doesn't consider every element in the set. So that's a qualitative difference between binary search and linear search. Linear search necessarily considers everything, and binary search doesn't. Now that doesn't mean that linear search is bad. Sometimes you actually have to consider everything, because sometimes you can make no assumptions about the underlying stuff. So binary search is fast in part because it can make assumptions about the underlying data, in particular that it's sorted. Whereas linear search cannot make assumptions about the underlying data and therefore considers everything. But it's also more thorough as a result. So when we think about these two different kinds of searches, it's useful to think about them as like, okay, well, I have two kinds of searches that I learned. But more importantly, it's important to think about them as metaphors for more sophisticated kinds of searches. So when you, in the future, consider algorithms that perform searches, you of course want to have things that are fast, and you want to have things that are thorough. Linear search and binary search sort of illustrate the idea that you can have thoroughness if you have assumptions, or you can have thoroughness if you're just exhaustive. But you can't have both at the same time. Finding ways to trade these off and performing the search on huge possible spaces, spaces that are too large to store all the data even on many hard drives, becomes the kinds of problems that people perform search on now. So let's start with linear search. Linear search can be implemented by you guys right now, and it's important to understand just how exactly it works and to understand the conditions that it requires. So linear search begins with an array, and let's just imagine that we're searching for integers because it doesn't really matter what we're searching for. And in the context of this class, that means that we could be considering arrays of any type, and we could be considering quantities or qualities of any type. So rather than searching for integers, which is a nice example, we could be searching on the lengths of strings. We could be searching on the number of the letter A in a string. We could be searching for the number of times a certain value is divisible by some other value, and so on and so on and so on. There are lots of possibilities that we can search for. But let's just imagine that we're searching for a specific thing. We're searching for an integer equal to 1. So the way linear search operates is that it is simply a loop that examines each member of the array to identify a member that's equal to 1. So imagine that we have a for loop for I equal to 0, I less than list1 dot length, I plus plus. If list1 sub I is equal to 1, return the current index, otherwise don't. Otherwise continue. So here what we have is that process. Step 0 considers the first array member of the array. Step 1 considers the second member of the array. Step 2 considers the third member array. And then finally, we identify it in the fourth member of the array. Pretty straightforward. So for those of you who are sort of thinking about this like, oh, linear search is easy, I got it. That's great. The basic principle is easy to understand. But I encourage you to not stop there. Because this is a principle that, just like the other principles in this class, I will expect you to be able to apply in many different ways. So linear search doesn't have to be applied in a linear search of an array in the order of the array. Perhaps for some reason I want to perform a linear search in some other order. Why would I want to do that? Well, maybe I know something about the order of the members of the array that I can't exploit with binary search, but I still want to search exhaustively for. So, for example, imagine that I had a list of the students at Lehigh University based on their LIN number, right? A big array of integers that was just a bunch of LIN numbers. And imagine that the list that was provided to me idiosyncratically happened to be I don't know, ordered boy, girl, boy, girl, boy, girl, or something like that. And if I wanted to perform a linear, or if I wanted to perform any search to identify the person with, say, the highest Lin number, I could just do the linear search that I had here. But if I wanted to perform a search for the boy with the highest Lin number, then I'd have to consider only every other member, right? In order to perform an exhaustive search, then I have to think about how I modify my for loop in order to exhaustively cover every other member of that array to search efficiently, to search correctly, because I'm only trying to consider every other member. So there are many variations on the way that we can perform linear searches. Some of them seem arbitrary, like the examples that I make up off the top of my head in class. But there are reasons for having linear searches that are not this basic search that I have here. And so for that reason, I encourage you to think about how those variations can happen. Okay, so how do I implement this? Generally, this is implemented with a for loop. The reason why this is implemented with a for loop is because one of the simplest variations on linear search is that you're only considering a range of the array. So again, let's go back to the array of Lin numbers of Lehigh students. Imagine that the way that the array was populated, I populated the Lin numbers of students each year as they came in. That each class of freshman students got populated into the array each year they came in, and now the array is 25 years old, and it's got all of these students in it, and generally it's got the students in a certain order, in a class-by-class order. So if I happen to know where the beginning of one class started and the end of that class started, then the way that I could make my search faster would be to only search through the part of that array that corresponded to the class that I was looking for, right? So the reason why a for loop is frequently used for linear search is because I can start with the beginning of the search at a particular point in the array, and I can end it at a particular point in the array, simply by modifying the endpoints of the for loop. I can say for I equal to 45,545, I less than 48,446, I plus plus, search linearly for this member, right? So I can make variations on the linear search very easily with the for loop that let me control closely the range that I search in. So in general, the for loop will look at every member of the array, starting from the beginning. If that member is equal to what you're looking for, break out of the loop. Otherwise, continue. And set a Boolean variable called founded if it's equal to true. So if you're implementing a linear search, sometimes you simply want to know if that member is in the array. Like we want to know if there's a member in this array that's equal to 1. But sometimes you want to know where it is, right? So sometimes you want to return the index of that member in the array so that you can find it again later, or that you can return other information about it later. So one of the things that we frequently use array search for is that we will use arrays to store indices where we can look things up later. So I might have, you can imagine that the array is kind of a card catalog. It stores the, say, storage locker number of some information that I'm looking for. I can search for the storage locker number in my array, and then I can go find it in the storage facility. Okay, so let's look at binary search. Binary search is different from linear search because it skips elements of the array. So if it skips elements of the array, then it works very differently from linear search. So let's look first at how the algorithm works, and then we'll think about how to code it. So if the goal of binary search is to find a member equal to 8, and it relies on the fact that the array is sorted from smallest to largest, then the way that binary search will do this is that it will first look at the middle member of the array. So how does it look at the middle member of the array? Well, it takes list1.length and divides by 2. So it knows what is the middle member of the array. So it first looks at that middle member and it asks, is that the value of that middle member larger or smaller than the thing that it's looking for? So it's looking for the number 8, and it knows that the array is sorted from smallest to largest. So because the middle member is equal to 4, it knows that if the number 8 is contained in this array, it must not be before the number 4, it must be after the number 4, because this is provided in sorted order. Yeah?
In a binary search, do you assume that each number only appears once?
That's a great question. So the question was, in a binary search, do you assume that each number only appears once? And you do not assume that. So it could appear multiple times. It doesn't affect the algorithm. If there's some way to distinguish between things that appear multiple times, then you might have to make a variation of your search, but it won't affect this fundamental thing where you check the middle and okay, so that's the first step. You check the middle of the array, and you decide whether or not the thing that you're looking for is above that member or below that. What you do next is, after you've decided if that member of the array is above or below where you are, you look at only that half of the array. So, well, I mean, I guess you could stop if you found it in the first try, but let's assume that you don't find it in the first try. Then you divide the array into 1/2. And in this case, the new bounds of that array are the next member of the array before the 1/2 position and the top member of the array. And you ask the middle member, see if it is equal to the member that you're looking for. And here we have an interesting case. There's only 4 members of this array, right? If there's only 4 members of this half array, then what's the middle member, right? If you divide it in half, then you get 2 equal halves. So the middle member, we can say, just by convention, will always be the lower of the 2 halves, or the upper, the lower of the 2 possible middles, or the upper of the 2 possible middles. That's a convention that could, at most, make your binary search check one more time. But it's a useful thing to know. So in this case, let's assume that we always check the lower middle array member, and in this case, it's equal to 8, so we found it, and we're done. How exactly do I implement this? If I can't do it with a loop that's going to step through the array the way that a linear search does, then it's a little bit strange how I might do this. So let's look at how this works. Divide and conquer goes to look for the middle of the array. And if that's what you're looking for, then you're done. And if not, you need to figure out what the new array area is, the new search area is. When you're looking at the lower half of the array, then it's from the original beginning of that half of the array to the element up to the middle element that you looked at so far. And if it's the higher, then it's the higher half. So what you have is you have a loop, typically a while loop, that continues until the upper part of the array being considered and the bottom part of the array being considered become the same thing. Once they become the same thing, then you're done because you've performed one more check and the calculation is complete. So let's look at this in a little bit more detail before we look at some code. So this possibility is going to be harder to find because the member of the array that we're looking for is all the way out on the edge, and that will require us to divide the array into several halves. So here we're looking for the number 19, and we start off by looking at the middle, which is, sorry about my array indices repeating here at the bottom. But we start looking at the middle, we see that 6 is not equal to 19. It's also less than 19. So we divide the array into 1/2, starting above the 6, right? We considered the 6 already, so we don't need to look at the 6. We know that the number 19 is strictly above the array in this half. So now we have a new range. The range is from list 1 sub 6 to list 1 sub 10. We find the middle member of that. That's list 1 sub 8. List 1 sub 8 is equal to 11. It's not equal to 19. So again, we divide in half. we take the upper half, this 1 sub 9 and this 1 sub 10, incorrectly indexed here in the figure, are all that remains of this array. So we look at the half of this, and let's pretend that we look at the upper half of this, and so that helps us find the number 19. Now we've had 3 iterations through this loop, and you can kind of see how each time we run this loop, we start with what's defined as the bottom member of the range that we're looking at, what's defined as the top member of the range that we're looking at, and what's the middle member of the range that we're looking at. So once we find the middle member of the range, we check to see if it's equal to what we're looking for, and then we update the top and bottom. So if the middle member of the array is 6, and the top and bottom, the middle member of the array is index 5, and the top is index 10, and the bottom is index 0, since list 1 sub the middle member of the array is not equal to 19 and less than 19, we're going to update the bottom end of that array to list 1 sub 6. So the bottom end becomes list 1 sub 6, and the top end becomes list 1 sub 10. When I check again, and again, I'm sorry about these indices being wrong. When I check again, list 1 sub 8, the middle of the array, is not equal to 19. So we update the bottom of the array to the one member of the array that's above the middle member, and we have a new array. So the structure of this code is going to be a while loop, and it's going to check to see what the range of the bottom and the top of the array is. Each time we find out what the middle is, we switch the bottom and the top members of the array that we're considering to be smaller and smaller and smaller until we find the number that we want. I thought there was code here. Okay. Let's write some code. We have time. Okay, so while I'm waiting for the container to restore, does anybody have any questions about binary search? Greg?
Can you combine binary search and linear search?
Yes, yes, you can. In fact, it's frequently done. So one question is why would you combine binary search and linear search? It turns out that binary search in the last few iterations, when you're considering just a few members of the array, is sometimes slightly slower than linear search. So sometimes what they'll do is when people are trying to write a slightly faster search, they'll binary search until the range that they're considering is within, say, 20 elements, and then they'll just for loop through the rest. Other times you have a statistical reason for thinking that the thing that you're looking for in the binary search is at the beginning of the range that you're looking at. Maybe because you know that there's some separation in the data where the values in the array members are not going to be super close together or super far apart, like they're evenly distributed. And once you see that it's in the sort of beginning part of that range that you're looking at, you might start linear searching instead of binary searching. So one of the ways that people sort of hack together slightly faster searches, they're not theoretically faster because obviously you could be ultimately slower if you guess wrong with switching to linear search. The advantage here is that if you have a hunch, you can make it a little faster. Okay, so is this too small? Let's make this a little bit bigger. That's kind of ridiculous. Okay, so let's start off by making our array. So int test is equal to new int. What's a big number? 100. Or I'm just going to fill out this array. With, let's say we'll fill it up with like multiples of 3. So this will be my test array, and I'm going to run binary search on it. Test, and let's say we're searching for the number 45. Sorry. Okay. All right, so we're going to implement binary search. The way that we implement binary search, and I may screw it up slightly, is we will have two variables that will represent the bottom and the top of the array range that we're considering. So int, let's call it min, is equal to 0 always, because it's the beginning of the array in the beginning. And int max is equal to the length of the array. So array dot length. Let's not call this array. Let's call this input. Okay, so input length minus 1. Okay, so this is input length minus 1 because we want it to point to a real member of the array. So remember that the indices of the array run from 0 to the length of the array minus 1, and not to input dot. Okay, so the conditions for searching will be while min is less than max. And we'll do the following. So first, find the middle. What is the middle? The middle is equal to the max minus the min. Divided by 2. No, excuse me.
Isn't
Min.
it max plus min?
Yes, you could write it as max plus min divided by 2, or min plus max minus min. I think this is, well, all right, so to me this is more intuitive. To other people, max plus min divided by 2 might be more intuitive. So let's write it both ways, just so everybody can see it. So does everybody see why it could be one or the other? I mean, obviously you can convert one into the other, but min is the beginning of the part of the array that you're looking for, and max plus min is half of the array, so you're adding 1/2 to the beginning. So that's why this is more intuitive to me, but you could also say that you're adding the max and the min divided by 2 because you're getting the average of the max and the min. So those both work.
Would you need to make that an int as an argument?
No, you don't have to make this an int because if it's an odd length and because there are integers already, it will automatically truncate to an integer. And it should be noted that there's an assumption here. So the assumption that's built into this code is that we want the middle array member to be the lower middle of the two middle members if there's an even length array. So let's look at the example here, right? There are 10 members of this array. Well, there's 11 members of this array, 0, 2, 8, 9, 10. So there's 11 members of the array, and this is the middle member because it's an odd number. But here, oh, this is 5 again. All right, so imagine that there's 10, right? If there's 10 and this guy isn't there, then it's between this one and this one as being the middle members of the array. Your convention just has to be uniform. Choose one or the other. So if you always divide the length in 2, then it's the lower member. And if you divide the length in 2 and add 1, then it's the upper member. So this is the lower member. I'll comment this out. Okay, so let's find out what the middle value is. And if the middle value is equal to the thing that we're searching for, we'll return the index. Just to say that that's where we found it. Okay, so if we don't find it, if this is false, then we're going to figure out how we search it. Yes?
When you want to return mid instead of mid-val, because you're looking for that.
Excuse me, yes, you're right. We want to return it. Thank you. Now we want to, okay, so if we're at this point of the code here where I've highlighted, then mid-val is not equal to search, right? Because we would have returned otherwise. So since mid-val is not equal to search, what we want to do is we want to update min and max so that we can search again. So in this case, min, if mid-val is less than search, and here we're assuming here we're assuming that the array is increasing in values. So if we're assuming that the array is increasing in values and mid-val is less than search, then what we want to do is we want to look at the upper half of the array, right? So we'll update min equal to mid plus 1. Max doesn't need to change because it's still the upper half of that array range that we're considering. But the min, because we know that we're looking at the upper half of the current part of the array that we're looking at, we want to update that to mid plus 1 so that we can go from the whole array to the upper half. Now, you can have an else statement. That's the case where mid-val is less than search. Mid-val is not equal to search because we caught that up here, right? So the only possibility is that mid-val is less than search. I'm sorry. That search is less than mid-val. Sorry. Then in that case, we'd update max equal to mid minus 1. So what we've done is we've taken the range. We know that the mid-val is greater than the search term, so we update the range to be the lower, right, from the top. We update the top to be lower because we're looking at the lower half of the range. Just to put this all on one screen, I'm gonna make my code a little bit ugly. Okay. So now we've updated the max and the min, and we're ready to continue. So before we test this, let's first think about the case where this finishes. So at some point, mid and max and min will be very close together. They'll be, say, 1 apart. So when max and min are 1 apart and we don't find it, let's say that the member of the array that we're looking at is not in the array, then we will set one of them equal to mid or to max and subtract 1. And they should be equal. Now, it's possible in the code here that I have messed this up slightly, and because of the way that we divided half, I may not cover one of the cases correctly. We'll see that because if I didn't cover that correctly, it will run forever. So let's test this out. And in order to test this out, we will have this printout here. And this is a standard way that people debug their code when they're writing a loop. They write the status of the loop either at the end of the loop or somewhere in the middle of the loop, just to figure out what the variables are equal to as the loop is running. So if my code starts running forever, then it's not going to just be a blank screen just having me wait forever. It's actually going to be printing out what the max, min, and mid are each time. So here, let's do that. So min, mid, max, mid. Excuse me. Oh, thanks. Min, mid-val, max, and great. Okay, so I don't know if this is going to run the first time, but let's see. Now, with this test, we're running at multiples of 3, right? So multiples of 3, searching for 45, should find it. Because this is going to be, it's going to be 0, then it's going to be 3, then it's going to be 6, then it's going to be 9, and eventually it's going to be 45. Oh, okay, I'm missing a return statement. Yeah, there's the case where we don't find it. So if we exit the while loop and we don't find it, we're going to print it out. Didn't find it. And return -1. So if the return value is -1, then we know it's not in the array, so we didn't find it. Let me fix the printouts a little bit. Do we print out if we find it? No, we don't. Okay, so you can see the way that it's searching. 0 is the beginning. That's really weird. It looks like our max is wrong, right? Our max should start off at 99. There's 100 members here. Oh, okay. It's after we updated it. So here we can see that the min was 0, the max was 99, the middle value was 49, and the number that was there is 147. So 147 is larger than the thing that we're searching for. And we're searching for 45, so that we're going to use the lower range of the range that we're searching for. So then we do this again, min at 0, max now at 48, because we divided it in half. And the mid is 24, mid val 72, and that gets repeated and repeated until we find it at array number 15. And it makes sense that it's at array number 15 because the first one is 0, the second one's 3, the third one's 6, and eventually 45 is the 15th one, the 16th member. Okay, so let's look at another possibility. Let's search for something that's not there. So we have 100 members, each one is multiplied by 3, so the highest member is probably something like 300. So let's say we search for 500. So here we can see that we update the min and the max. Each time we increase the min a little bit more as we zoom in on the final possibility, and at the end, we don't find it. So I haven't tested this thoroughly, but it looks kind of okay. Let's try looking for a member that's definitely not in the array, but is within the range. So not a multiple of 3, but between 0 and 300. Does anybody want to give me a number?
2.
2, okay. All right, so it didn't find it, that's good. You can see it divided the ranges down, 48, 23, 10, 4, and 1, and it didn't find it. I'm actually kind of surprised that I didn't mess it up the first time. But I can send you guys a copy of this code so that you can see a while loop running binary search. You can also Google for this. This will be up in a million different copies somewhere. I'm glad that we had a chance to